This is the second part of Lecture 6. Here we're going to talk about entropy of mixing. In the first part of Lecture 6, we talked about how to calculate entropy changes when there were, for example, heat transfer to or from a system or PV work being done on or by the system. In this part of Lecture 6, we'll be talking about the entropy of mixing when in fact there's no energy change within the system. Alright, so let's sort of set that up well, this is the equation we want to get here, and let's set that up by drawing a picture. Alright, so suppose we have two gases, and let's make these gases argon. We'll separate two volumes here, put argon over there and put helium over here. Argon will occupy some volume argon, and this will occupy some volume helium. And there's a partition between the chambers in this system, so it keeps all the helium over here and all the argon over here, and what we're going to do is remove that partition. This will be some temperature, say, of argon, some pressure of argon over here, some number of moles of argon over here. Same way here we have temperature helium, pressure of the helium, and the number of moles of helium. Let's assume that the temperature of argon is equal to the temperature of helium, so there's no temperature gradient. The pressure of argon is equal to the pressure of helium, so there's no pressure gradient. And of course the number of moles will be different between the two systems if the volumes are different. Alright, so what we're going to do is to remove this partition, just take it away magically. And what we're going to end up with is argon plus helium mixed, and the temperature will be the same as the temperature before removing the partition, as will the pressure. Now there's no gradient in temperature here, so there'll be no transfer of heat between these two chambers. There's no pressure gradient, so there'll be no transfer of volume between them. The volume, is different here, but when we remove it, we'll have a total volume. So there's really no work being done, nothing going on here. But what we find is that, in fact, the argon diffuses into the helium diffuses in the argon, and at the end of the process, when it reaches equilibrium, the argon and helium are mixed. There's nothing driving this. According to the first law of thermodynamics, there's no gradients in temperature or pressure. Nothing going on here, but nonetheless this process happens spontaneously and only in one direction. You never see the argon in this system spontaneously collecting over on the left, and you never see the helium spontaneously collecting over on the right. And this is an example of why we needed the second law of thermodynamics. So to describe why this only goes one way, we're going to calculate the entropy change, and we'll find the entropy change for this process is positive, so entropy will increase, and the second law of thermodynamics predicts this will be a spontaneous process. Alright, so how do we calculate the entropy change? There's no work or heat being done on or by the system or anything. Well, there is a volume change. Here argon is constrained to this volume. When you remove the partition, argon now has the entire volume to move around. And the same way with helium. So how can you, this is interesting. Wonder why that happened. Okay, so let's do that calculation. So remember that to calculate the entropy change when volume changes, that's just NR times the natural log of the final volume divided by the initial volume. Let's do that calculation for argon for the system in the previous slide. So delta S is the number of moles of argon times R times the natural log. Let's see, the final volume is the total volume, the sum of the two volumes before we remove that partition. So this will be the total volume. And the initial volume, argon was constrained to move in this volume here. So that'll be the volume of the argon. And we can write a similar equation for the entropy change for helium. That'll be the number of moles of helium times R times the natural log of the total volume divided by the volume that helium initially occupied. Okay, so entropy is a state function, so the entropy change going from here to here is the entropy change of the argon plus the entropy change of the helium. So entropy change is the entropy change of argon plus the entropy change of helium, and just equal the number of moles of argon times R times the natural log of the total volume divided by the volume of argon plus the number of moles of helium times R times the natural log of the total volume over the volume of helium. Let's pull R out. R is a constant. Pull that out of the sum. This would be R, number of moles of argon times the natural log of the total volume divided by the volume occupied by argon plus the number of moles of helium times R times the natural log. Ooh, we pulled that R out. Ooh, forgot about that. Sorry. I love that eraser function. Just get rid of all your mistakes. Times the natural log of volume total divided by volume helium. It'd be nice if life had an eraser function. All right, so that's what this is. So we just got that equation there. Let's introduce this term here. This is called the mole fraction of A. That will be defined as the number of moles of A divided by the total moles. All right. This is the Greek letter chi, and this will be called the mole fraction. That's a unit, a concentration unit that was introduced in introductory chemistry. All right, so if that's the case, then let's go down here. This is a process that has constant temperature and pressure. This implies from what's the name, Avogadro's law, that the volume occupied by, say, argon divided by the total volume is equal to the number of moles of argon over the total number of moles. I just all right, that can be just, and we're assuming now an ideal gas. Okay, so from Avogadro's law, that's what we get. So let's rewrite one of these expressions, say delta S for argon, we said was N, number of moles of argon, times R, times the natural log of the total volume over the volume occupied by argon. That's equal to the number of moles of argon times R times the natural log. Look, volume of argon over volume total. This will be defined as we said in the earlier, the mole fraction of argon. So this would be 1 over the mole fraction of argon, or taking the inverse of that, that brings a minus sign over here, the number of moles of argon times R times the natural log of the mole fraction of argon. And similarly for the change in entropy of helium, that'll be just the minus number of moles of helium times R times the natural log of the mole fraction of helium in the final mixture. So that the total will be the sum of these two, and let's pull out the R from the sum. This would be minus R times the number of moles of argon times the natural log of the mole fraction of argon plus the number of moles of helium times the natural log of the mole fraction of helium. All right, so this is another way to write the expression of the total entropy change, and that's what this one is here. All right, so we've got a couple ways to calculate entropy changes when things just mix and there's no energy being transferred forward or backwards. And we expect that the entropy change for this will increase, so we expect that this will be a positive number. Note that mole fractions are always less equal to or less than 1, so this will give a negative value. The log of a number less than 1 is negative, and that will cancel out that negative. This term will be positive, that term will be positive, and so on. So you will get a positive entropy change. Okay, so let's do a problem to illustrate what we've just done here. This is a problem 3.23 of Ball. We have 4 liters of argon and 2.5 liters of helium, each at 298 and 150 atmosphere. They mix isothermically and isobarically. So constant temperature, constant pressure, just like we talked about in the previous slide. The mixture was then expanded to a final volume of 20 liter at 298. Determine the change in entropy for the complete process. So it looks like we have 2 contributions to entropy. First, we're mixing the 2 gases, and then once the gases are mixed, we then are expanding them. Okay, so entropy is a state function, so we say that the total entropy change will be the entropy change due to mixing plus the entropy change due to expansion. All right, we just talked about how to calculate entropy change of mixing. So the entropy change of mixing, that'll be the entropy change of argon mixing plus the entropy change of helium due to mixing. And so we have a couple ways, a couple equations to use. Which one should we use? Well, let's use this one, although you could, if you want, do it yourself. You can use this one too, mole fraction. But let's use volumes just for fun. All right, so delta S for argon mixing will be equal to plus, this is a plus, number of moles of argon times R times the natural log of the volume total divided by the volume occupied by argon. The number of moles of argon, let's see if we can go back and find that out. Not given. However, the volume, the temperature, and the pressure of argon are given, and we're assuming an ideal gas, so that we can use number of moles of argon is the pressure times the volume divided by RT. The pressure was 1.5 atmosphere. The volume of argon, let me just check that, 4.0 liter. R, appropriate value of R is 0.0821 liter atmosphere per mole Kelvin. And the temperature, absolute temperature given in the problem, 298. And plug this into our calculators, and what we find is, what did I get here? 0.245. All right, so there's the number of moles of argon. R we know. Total volume. See, what's V total? Well, what we're doing is we're mixing 4 liters and 2.5 liters. So the total volume here is 6.5 liters. So delta S for the argon, it's the number of moles of argon, 0.245 mole, times R, 8.314 joule per mole Kelvin, times the natural log of the final volume, 6.5 liter, over the initial volume. Initially argon was in 4.0 liter. And so this comes out to be 0.989. You do the same kind of calculation for helium. You can do that on your own if you want. And by the way, what are the units here? Moles cancel out. This is unitless. This is joule per Kelvin. Do the same thing for helium. It's 1.21 joule per Kelvin. Note that the entropy change of mixing for helium was greater than that for the argon. And this is an ideal gas, so you cannot explain the difference due to the difference in properties of argon and helium. So why is that? Let's look back here. Helium initially was at 2.5 liters, and it now expands into 6.5 liters. That's a bigger expansion, a lot more volume for helium to expand in, and therefore the entropy change for helium would be greater than that for argon. Argon goes from 4 to 6.5 liter, not as much volume change as helium, so helium would have the bigger entropy change, and that's what we find. So that the total entropy change due to mixing is 0.989 plus 1.215, or, now maybe I should reduce some significant figures here, 2.20 joule per Kelvin. All right, so that's what delta S for mixing is. And we said after we mix, then we expand it. We expand it from our combined total volume after mixing, 6.5 liter, to 20 liter. And again, same temperature, but we're just changing now the volume, which implicit means we're changing the pressure. Okay, so now for the second stage. So delta S, now we're going to calculate for the expansion. That will just be the number of moles, and now we have a mixture. We have argon plus helium, so it'll be the total number of moles times R times the natural log of the final volume, which you said was 20 liter. The initial volume was 6.5 liter. Total number of moles, we showed the calculation for argon, 0.245 mole of argon. And if you do the calculation for helium, which we didn't do, but we left to the reader, 0.153 moles of helium. So that's the total number of moles. R, 8.314 joule per mole, I'll omit the units here, times the natural log of 20 over 6.5. And you plug all this into the calculator and you get 3.72 joule per Kelvin. And therefore the total entropy change for both processes would be the entropy of mixing plus the entropy change for expansion. And the mixing we found was 2.20 joule per Kelvin, and the expansion was 3.72 joule per Kelvin. So the total comes out to be 5.92 joule per Kelvin. All right, so that's how one uses the entropy of mixing in order, or how one calculates the entropy of mixing if you're just taking two gases and mixing them together. All right, that's the end of this part of the lecture.